We're going to be solving Cambridge IGCSE Chemistry Paper 6 Alternative to Practical October-November 2025 Paper 61. The first question states, hot concentrated hydrochloric acid reacts with solid manganese IV oxide to make chlorine gas. We don't know this reaction. This reaction is not part of the syllabus, but since examiner is telling so, okay. Let's see what happens next. Chlorine gas is toxic, okay, and more denser than air. Concentrated HCl is corrosive. So now they're telling us some important information that the chlorine gas that you're making, to make chlorine gas is kind of toxic, right? And it's more dense than air, okay? Concentrated HCl is corrosive. Figure 1.1 shows the apparatus used to make and collect the sample of the chlorine gas. There is one error in the way the apparatus has been set up in figure 1.1. Okay, so this figure 1.1 apparatus is a faulty apparatus. We got to figure out the error. I believe that if you guys know this thing, that when something is denser than air, that means we don't collect it by upward delivery, we collect it by downward delivery. Why? Because if it's more denser than air, look, what's going to happen is that I'm going to explain this to you. Chlorine is more denser than air. And when something is more dense, it falls down. And it's going to fall out of this test tube. It's not going to be collected in this test tube. It's going to fall out. So what you got to do is, in order to make this apparatus work, you need this to be downwards like this and then collected in a test tube, something like this over here. Chlorine gas can easily be collected because it's more dense, it's gonna sink downwards, right? That's the problem here. Name the item of apparatus labeled X. X is a simple conical flask. You should learn all flasks, conical flask, round bottom, flask, every flask, okay? This is a conical flask. Undisputedly, you should know it has a cone shape, something like this, a cone shape. That's why we call it conical flask. Identify the substance labeled Y. Y. Okay, so what's happening is you got to look at the reaction. Hot concentrated HCl reacts with solid manganese oxide to make chlorine gas. So over here, you can see something. At the bottom, you can see something solid. Can you see the solid layer at the bottom? This solid layer, right? And can you see the liquid that you're dropping from the beaker above? So that liquid must be hot concentrated acid. And this solid must be manganese oxide. So I guess there is no dispute in it that it's concentrated hydrochloric acid that you're dropping from above. You know what? I'm going to tell you guys one thing. The ATP paper is easy for those people who don't study theory, who don't study the MCQs thing. They're good with the ATP because ATP is a paper where you can lose marks you don't know and you can gain marks you don't know, right? Because there's no specific syllabus. It's just practical skills. Concentrated hydrochloric acid. And you know, the people who are good with studies, they usually suck at ATP. Why? Because they've learned everything. They can score full on theory. They can score full on MCQs, but ATP, it's a chance that they might mess up something. Because ATP is more about being on the spot in the paper rather than learning things before. Okay, name the item of apparatus that can be used to heat X. Bunsen burner. Anything you gotta heat in a chemistry experiment, you gotta use Bunsen burner. And you're gonna place Bunsen burner flame over here. It's gonna look something like this, and then whatever. There is one error in the way the apparatus has been set up. Describe a change that needs to be made for the apparatus. I just told you that this test tube needs to be inverted. So describe the change. The test tube needs to be inverted downwards, right? Downwards or other way around. So that's the biggest problem which I faced, right? We need to use the downward delivery method. not the upward delivery method. Explain why the experiment should be carried out in a fume cupboard. A fume cupboard is used for all chemistry experiments in which a toxic gas is going to be released. Wherever you have toxic thing being produced, use it in a fume cupboard. So over here, we're making chlorine gas. Chlorine gas can kill you in no time, right? So we're gonna tell them that chlorine is toxic, man. A student investigates the reaction between dilute hydrochloric acid and aqueous sodium hydroxide. The student does 5 experiments. Experiment 1. Fill a burette with aqueous sodium hydroxide. Simple titration is going to happen, I think, because what we're doing, we have our typical dilute acid, we have our typical alkali, and we're just doing titration. For titration, what do you need to know? Look, this is all steps for titration. All titration. Experiment 1 is titration. Experiment 2 is again titration. Then you repeat your titration, or I don't know what you do, and then they ask you questions about it. So if you're running out of time, okay, I don't recommend it, but ATP paper, if you're running out of time, because the time you have for this paper is like 1 hour, and if you're short of time, like if you don't figure out something above like like chlorine is toxic or this thing you don't figure out and you're out of time, you can just quickly don't read it, only if you're out of time. That's not recommended, and quickly skip to this part, right? But we're gonna read because we're good to go. Okay, fill a burette with aqueous sodium hydroxide. So one thing you're going to take in the conical flask and one thing in the burette. This is your conical flask and this above is your burette, right? This is your burette, and in the conical flask, we don't know. In the burette, we have taken sodium hydroxide. Let's read further. Run some aqueous sodium hydroxide out of the burette, so that the level of the aqueous sodium hydroxide is on the burette scale. Record the initial burette reading. Use a volumetric pipette to add 25 cm cube of HCl into a conical flask. In the conical flask, we have our HCl in the flask. Record the initial burette reading. Okay, stand the conical flask on a white tile. Why do we use a white tile? So that we can clearly observe the color change of the indicator. Add 5 drops of thymophthalene. Thymophthalene indicator is going to be colorless in acid and blue in alkali. Please don't mess this up. Okay, indicator. Slowly add aqueous sodium hydroxide from the burette into the conical flask. Okay, now we're doing titration. Swirling the flask. Why do we swirl it? So that the contents are mixed. Every step is important. White tile, swirling the flask, just the solution changes color. This is the endpoint. Record the final burette reading. Okay. Experiment 2 say empty the conical flask and rinse it with distilled water. Why do we do it with distilled water? Because the moles don't change. In the conical flask, we have fixed moles, fixed volume, and the moles don't change in the conical flask. That's why we can do it with water, but for burette, we cannot do it with water. Remember, for burette, we wash it with the liquid that we have to pour in it. Please don't mess this up. Refill the burette with aqueous sodium hydroxide. Run some of the aqueous sodium hydroxide out of the burette so that the level of aqueous sodium hydroxide is in the burette scale. We're not washing it because we're pouring the same liquid into it. Okay. Record the initial burette reading. Use a volumetric pipette to add this off. Okay, now we're doing something else. Add 0.25 gram of sodium hydrogen carbonate. We're adding a base, remember, to the conical flask and swirl the flask. Stand the conical flask on a white tile. Okay. Doing an additional step, sodium hydrogen carbonate to the conical flask and swirling the flask. That's additional. And why are we doing this additional step? You got to know why are we doing this additional step. Because we gotta do something else, ठीक है? अभी आपको पता चल जाएगा. Slowly add aqueous sodium hydroxide from the burette. आपने base पहले acid में डाल दिया, मतलब कुछ acid ये base neutralize कर देगी, तो इसका मतलब है now will require less volume of sodium hydroxide. Everything should be on your fingertips, ठीक है? From the burette to the conical flask, swirling the flask until the solution, okay? This endpoint is gonna be at much less volume of sodium hydroxide. Why? Because some acid has already been neutralized by the sodium hydrogen carbonate. Repeat experiment 2 with 0.5 gram of hydrogen carbonate. अब देखें जिस बंदे को ये नहीं पता, you are increasing the amount of hydrogen carbonate. That means the amount of your alkali is going to decrease because the acid is already going to be neutralized by hydrogen carbonate. Okay. Use the information in the descriptions to experiment 1 and 5 of the mirror diagrams in figure 2.1 and 2.2 to complete the table. Okay, initial mirror treating. HCl was in the conical flask, right? So it's going to be fixed. The volume is going to be fixed. 25.0, 25.0, 25.0, 25.0, 25.0. Don't miss the zero, please. Final Burette reading, initial Burette reading. For experiment 1, the initial Burette reading is 0.6, right? 0.60. नहीं इतना नहीं लिखते, 6 तक ही लिखते थे, बिकॉज अब अपनी रीडिंग्स को आपस में वो रखें. ओके, फाइनल 46.1. ठीक है. Over here it's 1.123. That's the mistake I'm making. Bro, ये initial है और ये वाली जो है ये final है. That's the mistake I'm making. Please don't do this. Okay? Read 1.3 and this one's 41.123. 1.3, 41.3. Now we gotta calculate the volume. With this we need a calculator. Okay, 46.1 minus 0.6. 46.1 minus 0.6, 45.5. 41.3 minus 1.3. 41.3 minus 1.3, 40. 40 नहीं लिखेंगे आप, 0.0 लिखेंगे. प्लीज़ डोंट मेक दिस मिस्टेक. अगर आप अपने मार्क्स कटवाना चाहते हैं तो 40 लिख लें. इफ़ यू डोंट वांट योर मार्क्स टू बी डिडक्टेड देन राइट 40.0. 36.0 minus 1.4. 34.6. 24.1 minus 0.3. 24.1 minus 0.3. 23.8. 23.8. Done. 5 marks in on your paper if you just fill this up. Complete a suitable scale on y-axis and plot the results from experiment 1 to 5 in table point 1. And then we have to draw a line of best fit. No problem. Volume of aqueous sodium hydroxide added to reach the end point. Okay. Volume of, for 0 mass, how much volume we added? This is what we are. We have this. Okay. We have this. We have to plot this row against this row, right? If I am not wrong, these are the two rows we got to plot. So 45.5 for 0. For 0 it's 45.5. Okay, first I gotta see what's my lowest value. Lowest value is 13. Highest value is 45.5. So 0 है ये, 10, 20, 30, 40, 50. But if I'm 10, 20, 30, 40 and 50. But I need to remember one thing. What do I need to remember? I need to remember my figures. Please, इसको हम ऐसे नहीं लिखेंगे. क्यों हम इसको ऐसे नहीं लिखेंगे? Because हम नहीं चाहते कि एग्जामिनर किसी भी वजह से हमारे मार्क्स काटे. सो 10.0, 20.0, 30.0, 40.0, 50.0. भाई नहीं भी दिल करे ना, आके 1-2 zeros डाल दो ताकि आपके मार्क्स बच जाएं. अच्छा, 0 पे 45.5. दिस इज़ 45. दिस इज़ 45.5. 0.25 पे 40. 0.25 is going to be exactly over here. .5 it's 34.6. 0.5 it's 30. 34.6 is going to be somewhere here. At 1 it's 23.8, at 1 it's 20, 21, 22, 23, 23.8. At 1.5 it's 13, at 1.5 it's 10, 11, 12, 13. Okay, now I have to draw a line of best fit. Okay. I guess that's my line of best fit, right? And I can change its color. Do I have the option to? The sodium hydrogen carbonate added in experiment 2 to 5 neutralizes some of the dilute hydrochloric acid in the conical flask. The sodium hydroxide used in the titration neutralizes the remaining dilute hydrochloric acid. That was what I was telling you, that the hydrogen carbonate is going to neutralize some of the dilute acid and the sodium hydroxide is going to neutralize the other acid. That is why as the amount of your sodium hydrogen carbonate is increasing, it becomes 1.5, the amount of your alkali decreases because some of your sodium HCl is being neutralized by sodium hydrogen carbonate, right? Extrapolate the line on your graph in figure 2.3 and reduce the mass of sodium hydrogen carbonate needed to neutralize all the dilute hydrochloric acid in the conical flask. Extrapolate the line on your graph and reduce the mass of sodium hydrogen carbonate needed to neutralize all of the acid in the conical flask. Okay, so we need to find the mass that's going to neutralize all the acid. We have 25 of acid that is neutralized by 45.5 of aqueous sodium hydroxide. Okay. We have 25 of acid, 25.0 cm cube of acid. This is the point, because at this point we need 0 alkali. Do you understand why they gives you 0 here? Do you understand it? This is the point. It took me a while. It just took me 2-3 seconds to realize. It's such a lovely chemistry, so nice. Look over here. Look over here. This is the point. This is the point. This exact is the point at which you need 0 cm cube of alkali. So that is the mass of sodium hydroxide. I don't know if you get it or not, but if you get it, you're going to feel happy and proud. That is 2. This is 2.1, 2.2, 2.3, 2.4, 2.5, 2.05. That is what comes out to be my. So I'm gonna write 2.05 and grams, because that's the unit, right? Okay. Explain why the volumetric pipette is used rather than measuring cylinder to measure the volume. Pipette is more accurate than measuring cylinder. Just learn this line for ATP with that pipettes are more accurate than cylinders, and pipette can measure fixed mass, fixed volume. So we're gonna just tell the examiner that, look, pipette is more accurate than a measuring cylinder. Explain why it is not possible to use a volumetric pipette instead of burette to measure the volume of aqueous sodium hydroxide, because the volume is changing. Pipettes measure fixed amount of volume, right? Volume is changing. Look, for sodium hydroxide, your volume was kept on changing. If you look at the graph, this volume, then this volume, then this volume, then this volume, then this, pipette just comes in one fixed volume. So you're going to tell the examiner that volumetric pipette measures fixed volume, whereas in this experiment the volume of NaOH keeps changing. The conical flask is placed on a white tile to make the color change of the indicator at the endpoint more visible. Explain why universal indicator is not suitable. Okay, whenever you do acid-alkali titration, you never use universal indicator. An examiner is always going to be like, why are you not using universal? Because universal indicator gives a range of color changes. There's a lot of color change. Whereas when you are doing titration, you need the exact color change on the endpoint. Universal indicator is going to give you a mixture of color changes. So if you don't have the exact color change, you won't be able to determine the endpoint. So the problem here is they're going to tell the examiner that, look, when you use universal indicator, you know with universal indicator pH chart comes. Like for pH 2 it's going to give a different color, for pH 4 it's going to give a different color despite both being acids. Why? Because universal indicator gives a range of color changes. So you tell the examiner universal indicator gives a range of color changes. So it's difficult to determine the endpoint, right? Very difficult. Simple. Draw a line of figure 2.3 to show the results you would expect if the investigation was repeated using aqueous sodium hydroxide with twice the concentration. If you use it with twice the concentration, then the volume would half. Why would the volume half? Because twice the concentration means you have more moles, right? So then the graph would start, it would be a same line. Okay? I'm going to draw a line and then going to show you. It would be the same line, something like this. It would be a same line, something like this. Why aren't you flattening? It would be a line that's going to be of the same gradient, right? Similar to this, but it's going to be starting at, this is starting at 45 now. What's the half of 45? 45.5 divided by 2. It's 22. So it's going to start at 22-ish, 22. This line is going to start at 20, 21, 22, 22.7. It's going to be like this. It's going to be exactly at the half. Why is going to be it having a half the gradient? Because you got to realize that the concentration has been doubled. The volume is going to half because there are more moles, right? So you would require less amount of volume. Oh my god. I need to make it precision eraser and then I gotta erase this stuff. Okay, done. So this is my new line. And then examiner said label this line F. Here you go, examiner. A student tests two solids, solid J and solid K. Tests on solid J. Solid J is lithium chloride. Okay, thank you for telling it's lithium chloride. Now I know it's lithium chloride. Record the expected observations. The student carries out flame test. Oh my god, now I guess you're given with the flame colors, right? If you're not, then that's sad. you are. Lithium gonna give you red color. I don't think this part needs any explanation. Simply you're gonna tell if you put lithium on flame, you're gonna get a red flame. Red light, blue light. So we're gonna get a red flame. The student uses a roaring Bunsen flame to carry out. State why a yellow Bunsen flame is not suitable. Bro, if you use a yellow flame, that's gonna mask your color, right? The color change is not gonna be visible, right? And secondly, you know that blue flame is extremely hot. If you have ever experienced cooking on fire, would you have seen a fire that's generated from wood is yellow in color? It's less intense, right? The fire that comes blue in color, it's more intense. So yellow flame is not intense enough, it's not hot enough. So we're gonna tell it is not intense, or you can say warm. Not warm is a very cozy word. Not hot enough. Moving on. Student dissolves the remaining solid J in distilled water. Now you know it contains a chloride ion. They're gonna might ask for chloride ion test. To the first portion, the student adds 1 cm cube of dilute nitric acid followed by a few drops of aqueous silver nitrate. What do? We're gonna form a white PPT, then he's gonna add ammonia if I'm not wrong. To the second portion, the student add excess aqueous sodium hydroxide. Look, you have learned it that ammonia changes the precipitates, not sodium hydroxide, right? If he would have added ammonia, the white precipitates would have dissolved. But for sodium hydroxide, no change is gonna occur. Okay? Stick with the basics, right? Tests on solid K. Table 3.1 shows the tests and the student's observations for solid K. These are the tests. Heat about half of solid K in a boiling tube until there is no further change. Condensation forms at the top of the boiling tube. Hold anhydrous cobalt 2 chloride paper at the mouth. The anhydrous cobalt chloride paper changes color from blue to pink. Okay, doing a ton of tests. State the conclusion that can be made from the observation test 1. Look, what he did was he heated and he held anhydrous cobalt chloride paper at the mouth, and the paper changes color. It contains water of crystallization, right? It contains water. So that means the salt is hydrated. So we're gonna write we have a hydrated salt. That is what can be observed, what can be concluded. Two different cations can give the observations in test 2. In test 2, two different cations can give the observations. Okay. The remaining solid K dissolved in distilled water to form solution K. Solution K divided into 3 portions. To the first portion, add aqueous ammonia dropwise. A green precipitate form. The precipitate remains excess. Fe2 plus and Cr3 plus. Right? I don't think there's any dispute in it. If you don't know, go to the table below, it's written. But I've learned them, so I know Fe2 plus and Cr3 plus. Now what did you add? First, you add ammonia. Now, if you add NaOH, the Cr3 plus is going to dissolve, but Fe2 plus is not going to dissolve. Describe 2 additional tests that can be carried out on K to confirm which 2 cations you've identified in solid K. Simple, bhai, add NaOH, right? Excess NaOH. Chromium is gonna dissolve. Cr3 plus green PPT dissolves, and Fe2 plus remains insoluble. And one other thing you can do is always remember in the sheet it's written that if you have Fe2 plus, where's Fe2 plus? If you have Fe2 plus and you leave it to stand, it turns brown near the surface. So this can also be an additional test if you want. Identify the gas given off in test 4. Okay, test any gas given off. The gas turns lime, water, milky. I don't think this part even needs to be explained. It's carbon dioxide gas. Identify the anion in solid. Okay. To the third portion, I'd see a 3 cm cube of sodium carbonate. Effervescent scene. So carbon dioxide gas. That means you have an acid, right? You're dealing with an acid over here. It must contain H plus ions. Okay, to the second portion of solution K, but this is not the anion, this is a cation. Nitric acid followed by a few drops of barium nitrate, white precipitate, sulfate ion. This is all clear because you need to copy it from the table. Now we have a 6 marks experiment. Let's see what it says. When a solid metal is added to aqueous salt of a less reactive metal. Okay, so when a solid metal is added to a salt of less reactive metal, a reaction takes place. What do we call this? We call it displacement reactions, right? In metals, a more reactive metal is going to displace a less reactive metal from its salt solution. The reaction is exothermic and the temperature of the reaction mixture increases. The larger the difference in the reactivity of two metals, the more exothermic the reaction is. So the important bits they're telling us is that the larger the difference in the reactivity, the more exothermic the reaction is. Cobalt, manganese, and nickel are 3 metals which are all more reactive than copper. Okay, cobalt, manganese, and nickel are 3 metals which are all more reactive than copper and react with aqueous copper 2 sulfate. Okay, so cobalt, manganese, nickel, all more reactive than copper and react with copper sulfate. That means they're going to displace copper sulfate. Now we have to see which one is going to be at the top. Let's see what the question is. The temperature of the reaction mixture increases during each reaction. Plan an investigation to find the order of reactivity in which the temperature is going to increase the most. It's going to be most reactive. Okay, your plan should include how you use the results to find the order of reactivity of the 3 metals you're provided with the powdered samples of this copper sulfate and common laboratory apparatus. So what I'm going to do, I'm going to draw a diagram to make you guys understand what I'm going to do. So I need 2 minutes to plan out my experiment and then I'm going to So here's the experiment that I designed. I took fixed volume of copper sulfate in 3 different beakers. 3 samples of fixed volume. Then I measured the initial temperature of each beaker, 1, 2, and 3, right? And then I added fixed mass of each metal. Like in one I added the manganese, another I added copper, nickel, then I added zinc, and whatever the 3 metals were. And then I measured the temperature increase, like how much the temperature increased, and the highest temperature increase means the more reactive metal, and which there's lowest temperature increase, it means the least reactive metal. And the last thing you need to be careful about in this experiment, once you've mentioned the steps, you also have to tell the examiner the apparatus that you're using, right? So for the apparatus, you can mention a beaker or pipette to measure fixed volume, right? Apparatus is also important. Pipette for fixed volume, and then you can tell thermometer for temperature, right? So the 2 apparatuses, you can write thermometer and pipette. So that's the experiment, and you're just going to write this stuff in paragraph form.